Identification of disaster prone areas. That means what? In the bracket I put here susceptibility analysis. That means only we are addressing the spatial part, not the temporal aspects. Okay? The temporal aspects has to be always identified hazard assessment. Okay? But again, some hazard assessment also they use actually the triggering factor, one of the conditioning factor, and they don't do actually the temporal probability. Depends. In the literature you find a lot of kind of analysis. Okay, but the correct way of doing this spatial temporal assessment is always the hazard assessment. Okay. Now, so today this lecture, this is what we're going to understand. We'll learn about the susceptibility, the concept, then the elements of susceptibility analysis, the data, the input data, okay, and the most essential input data are, as I mentioned, is the inventory is always the most essential part. Okay, so inventory is the dependent variables, right? And then you have many independent variables, right? And we would like to know the spatial relationship between the dependent variable and all the independent variables. If there exists any kind of statistical relationship or any spatial relationship, that is what actually we are going to use in our model. Okay. Then we will also learn about conditioning factor and the frequency ratio model. We don't have much time because otherwise there are many models. Once you do the frequency ratio model, you can extend the model into other type of probabilistic model-based models, such as you might have heard weights of evidence model. Weight of evidence model is very popular in mineral susceptibility mapping or mineral perspective mapping, not susceptibility, mineral perspective mapping. Okay, very popular. We have also used it many times. So we have also some students from mining, right? So I can show you some examples how to do it, but as long as you learn one, you can be able to do actually apply for other type of application as well. Okay, site suitability assessment you can also use any kind of applications, like whatever applications I have mentioned in the first class, second class, or we can apply these kind of models. Okay. Now, if you want to define the susceptibility, what is susceptibility? Is basically it is the classification. That means for a given area, a study area, we would like to classify the area in terms of volume or different classes, different zones. That's why we call zonal analysis or susceptibility zones. Okay. So, and the degree, the varying degree of susceptibility to that particular type of hazard. Okay. So normally what we do, we put different color codes, right? No susceptibility, low susceptibility, moderate susceptibility, high susceptibility, and very high susceptibility. Now the question is whether to use 5 classes, some to use 3 classes, some to use 4 classes. I'll teach you what is the best way of doing it. Like the research that we have done it, based on that I'll teach you what to do it. So this is essentially a classification scheme, right? It could be volume or it could be area. But mostly we talk about area because we are doing 2-dimensional mapping, alright? And the spatial distribution of, we don't say disasters. Disaster is not the right word to use because we know, we have already understood, but for someone who doesn't have any background, they can understand, but we know already the definition of a disaster, right? Alright? Which exists or potentially may occur in an area. Okay? But again, once you prepare a susceptibility map, it's a static map, right? Because it's not a real-time kind of assessment, correct? Hazard is in real time. Why? Because the time footprint is there. When and where? The where can be changing. When can be changing, right? But in the case of susceptibility, it is a static output. But again, that also need to be modified if the new data comes in, right? For example, if the land use is changing, obviously one of your input variable is changing, right? So therefore, you have to do the assessment again. Alright? So, so that is one, the spatial footprint. Also it can be defined as a description of the velocity and intensity of the existing or potential hazard. Okay? For example, in the case of debris flow. Okay? So for different types of geohazard, obviously, there are different ways of presenting the output in the susceptibility map. Okay? So to perform the susceptibility analysis, two most important parameters are needed. Obviously, one is the inventory. Okay, the other one is the conditioning factors, conditioning parameters, or some people say as causative parameters, or some others also in the literature you can see they call what causative parameters. Actually, many people they say, but that's not causative parameter. That doesn't cause slope. Doesn't cause actually for a slope to fail, right? Because we have a triggering parameter anyway. So it's a conditioning parameter. The slope now is getting conditioned with a triggering mechanism. The slope and other variables actually they are getting conditioned to fail, right? Like saturation of the soil, or maybe the groundwater movement, and all these variables. Are you all getting me or not? If you understand this, you can apply actually to your own domain. Okay. Now, what do we do? Now we have to do a bit of modeling. Now we are slowly moving into the modeling steps. So to evaluate the time, robustness, and the inventory, that's why we have to analyze the historical data as accurate as possible. That's why I told you we must get just not only the spatial footprint historically, but also the time. When did it happen? Right? So now, again, when you pick up actually the locations, that is also very tricky. For example, landslide. You know how many of you understand the mechanism of landslide? There is a failure zone, there is a deposition zone, there is a flow zone, right? So now, when you collect that data in GIS, like what you learn collecting or picking up a point, picking up a polygon, right? As an inventory, let's say, assuming which one you would like to pick it out. That is what actually is going to determine also your assessment. Otherwise, it is going to be all wrong, right? So, in the case of landslide, obviously, you would like to take the polygon of the failure zone, not the deposition zone. Are you getting me? Okay? Maybe I can draw for you. See, let's say this is a landslide, let's say. Okay? This part is deposition, right? That means it is the toe end of the slope. It's already that the process has been completed, all the materials has come and deposited here. So when you do and you pick up the landslide of the entire area, that is wrong. Okay? Because remember, now you are doing the raster-based assessment, pixel to pixel correlation. So the correct pixel need to be identified as the landslide location. So this part is the failure area. Okay? So that need to be identified as the, if you are doing manually, let's say inventory is not available for you, even though if someone has the inventory, you must query. Let's say if you are getting the data from Geological Survey of India, right? They would have collected the data for their purpose. They have not collected the data for this kind of assessment. Maybe, you do not know, right? So therefore, you would like to do that investigation because, as I mentioned, it is the data quality plays very important role. Otherwise, you can be able to proceed and do all the assessment, but the result is going to be inaccurate. Understand? So you should not take also, this part is also, is not the landslide. Okay? But if you have more time, if you are preparing a very complete data set, you can first draw actually the entire polygon and then you take actually the point here. The center of the, let's say this is a big area, the center, depending on what is the pixel size, right, of your assessment. If you are taking 1 meter, 10 meter, so that means the 10 meter is 1 pixel, right? Are you understanding? Isn't it? So cell size is 10 meters means individual cell size is, pixel size is 10 meter. Okay? So depending on that, you have to do this. Now, if your landslide is very small, that means 1 meter. Now, you are doing your assessment in 100 meters. You are overtaking actually the area which not necessarily the landslide area. So that is why the spatial resolution plays a very important role. Are you getting me? Huh? So the scale plays very important role. Okay. Now, so what we do normally, when you do the modeling, in mathematical modeling, we know that when we have the given sample data or training data, we do not want to use them for all the training data actually for your modeling purpose, because we would like to keep some data for validation purpose. Right? Yes. Right or wrong? Yes. That's simple. But again, how to select those training data? That's a question. Let's say you have, for a given area, let's say you have 2,000 locations of flood or maybe landslide or any kind of any kind of application that you are working. Okay. Now, out of 2,000 locations inventory that you have, how would you select actually your training data? If you look at the literature, there is no standard procedures to follow. Okay. Mostly people take 80-20. That means they split the data into 80% and 20%. Okay. Then 80% of the data they use it for training the model or building the model. 20% they use it for validation. But there is no standard rule. Okay. Some of them they use 70. If you ask me, if you have more number of data set, I will use 50-50. Okay. So that means you have also a lot of data actually to do the validation in order to find that your model output is robust and is reliable. Okay? Now, how do you split the data? How do you split the data into, let's say, 70-30 or 80-20? You must pick it up randomly without having any human biases. Okay? And the data should be captured homogeneously throughout the entire area. Why? Because you have so many variables. Let's say you have 3 types of lithology. Okay, I'm just giving you the context of the landslide, okay? Because maybe I would ask you to do some simple analysis also using landslide data or forest fire. Also, I have got some data of forest fire. Okay, so let's say you have 3 types of geology. Okay, means what? Maybe granitic rock, you have some metamorphic rock, or maybe some sandstone or something like sedimentary rocks. Okay, and you have 2 types of soil maybe. Okay, clay type of soil, another time you have sand grain type of soil. Very big texture, large texture. So if you do not take your training data homogeneously, if one of these types of classes are being missed out, that is not being well represented in your modeling, right or wrong? So therefore, rule number 1 is they need to be picked up randomly without any human biasness, but you need to check. When you're asking the computer, it's not that just relying everything 100% computer. Then you take the data, overlay on it, take a look, see that actually whether it's being well represented with respect to all the input variables or not. Okay? Right? Then keep aside the balance 30% or 40% or 50% of the data as it is. Okay, clear? No. That is one way. If you do not have the time stamp of the data, that means if the temporal aspects of the inventory is missing, that means you know only the location of the inventory, but you do not know when exactly it has happened. Okay, then you use this process. But if you have a complete inventory, that means you have the footprint plus the timestamp, I would select actually my training data differently. How? Now let's say today we are in 2025. Now let's say we have 30 years of data. of 40 years of data going back to, what do you minus? 82. 35.
30 means 95.
30 years means 95. Okay, let's say 30. Okay, 30 years means 95. So what I would do, I would take 25 years of data, I would use it for training. That means until 2020, the data I would use it for training. 5 years, last 5 years of data, I would just keep aside for prediction. That is more accurate rate of prediction. That means you are predicting something from 2020 to 2025, and now you have exact data that has happened between these 5 years, which you can use it for validation. Getting me? Okay? So there are different ways depending on the completeness and the availability of the data set. Okay? Are you all with me? Okay, good. So I have already mentioned there is no standard ratio, then the training also I have already mentioned. This is what exactly I was mentioning, that the spatial distribution, the homogeneous distribution of the training data is extremely important. That's why to produce an accurate susceptibility map, it requires the proper spatial representation of conditioning factor. Okay? Also, in the case of landslide, although we call it a landslide, but again there are different types of landslides. It can be debris flow, and debris flow is totally different than normal landslide. Okay? Then if you have rockfall, it's totally different. So then you should split those data. You must do the assessment for a particular type of failure. Otherwise, assessment is wrong. Right? Because the characteristics are different. Because now you are looking at one as meteorological hazard. For example, the landslide mostly occur due to heavy precipitation. Okay, but rockfall, no. Rockfall sometimes it can also because of the passing of the heavy rainfalls. Or maybe there is one slope that you have unattended, left unattended. Now let's say there is a heavy traffic, or maybe there is a train going on, or maybe there is a simple, mild tremor that is happening. Also the rock will fall. Right? So therefore, you must understand the mechanism and characteristics of this area, and depending on the different area types, you must do the assessment. Okay? And based on that, you must optimize your conditioning factors. Which one to use, which one not to use. Some people, what they do, when they collect the data from an agency, okay, let's say geological survey, I should not say here, but let's say, but they have collected the data for a specific purpose. Okay, now if the landslide has happened in a very, very, what do you call, flat slope, less than 5 feet, I wouldn't even actually use that in my analysis. I would exclude those kind of data set from my measure, because that is going to give you a misrepresentation of the landslide. And they are like outliers. You may not have actually many, otherwise you are asking the computer to get confused. That's why I am telling you, you cannot use everything as it is in the computer. You must make all kind of assessment logical. You must interfere, you must check whether it makes sense, whether it's logical it makes sense or not. Okay? Are you all getting me?
Yes, sir.
Okay. Now go on. Okay. Okay, I have already mentioned. Again, I have also spoken about it. Many researchers they have used many types of conditioning factor, but doesn't matter. At the end of the day, you got to optimize it. Okay? And the finding, that's what I was mentioning yesterday. It was proven that Jaggur et al., Jaggur is my PhD student who graduated 10 years ago, that LiDAR data produces better quality than using too many factors. Too many factors doesn't necessarily actually give you a better result. Okay? Optimized factors actually gives you better result, accurate result. Okay? Now, let's look at one particular application, is the landslide. Okay? Okay? Good. So what are the things we have? We have many kind of parameters that you can use. Okay? Altitude is the height information which you can derive from DEM, digital elevation model. Slope you can derive from altitude. Okay? DEM aspect also you can derive from DEM. Curvature also you can derive from DEM. Stream power index also you can derive from DEM. Altitude you have to calculate. Okay, stream power index is, it's an equation that you take the total of slope of the upstream area and then the slope of actually the general slope of the area. That means you have to calculate actually the I think altitude. Okay. Then we have topographic wetness index, sediment transportation index, roughness index. All these variables all can be derived from the DEM. So one input data, but they have various types of variables that you could extract. So make sure your DEM is good. Otherwise, your error is going to be propagated actually through each of these variables or conditioning factor. Okay. Then land use land cover. How can you extract this? From satellite data. Okay. Then geology and then land use land cover should take from when? Let's say today you are doing the assessment. Okay. And you are doing the analysis for the 10 years. When should you take actually the land use land cover map? Not today. Because otherwise it's a misrepresentation of the area. So the time, temporal distribution is extremely important. At least during that period of time. As close as possible. Yeah, you can take that also. Okay? Geology doesn't change much. And lithology doesn't change anything. Today is sedimentary rock and then after 3 years it has become metamorphic, is it? No, right? No, right? Otherwise you will be having gold everywhere. Okay? So geology doesn't change. Fault lineaments doesn't change much. Okay? Then distance from fault, distance from river, distance from road, and NDVI, fluid density, and all other kind of data. And if you have more type of data, like forest information, okay, forest type, timber, okay, width of timber, okay, there are like some countries they have very detailed data, like Korea, they have everything is in 5,000 steps. Okay, so you can use those kind of data set as well. In India, I'm not sure what we have. Yeah, I think at a country scale, if I'm not mistaken, you have what, 50,000?
25,000.
25,000 is not too bad. 25,000 means it's about 10 meter. Pixel cell, which is fantastic. 50,000 is about 20 meters. So it's very good. For the whole country?
Yes.
I doubt.
In Google we have
25,000 for all kind of input variables?
not all kind of input variables. I'm talking about
Topo.
No, land use.
Language. Okay. But again, the question is how often do they update the map? That is also important. Okay. Let's say it's the 10 years old. But I think nowadays they must be updating because they are using the satellite-based information to automatically update the maps. They should have. But check. That means it's not just anyone can just give you one. Okay, here comes the land use land cover map. But you must do the analysis when the data was captured. Take a look. Do a bit of validation against the Google. What do you call Google Earth Engine, but Google Earth Engine gives you that timestamp, right? The temporal check, and also I would check also the inventory. Let's say the inventory will come, then I go drape it on the Google Earth Engine, see that whether there was a landslide maybe 7 years ago, 8 years ago, 10 years ago, because you can see the texture, right? Isn't it? So that is what you call research. Research is not actually collecting the data from anywhere and then just putting them in the computer and the dumb computer will do something and you get a dumb output. Right? So you must do the analysis, each and every variable. Okay? Good. Scale. Scale is very important. Okay? As I mentioned, so you must understand that the data, input data, scale is homogeneous. Okay. Now, when you classify, for example, the slope map. Slope is a continuous data. Altitude is a continuous data. Right? Altitude is a continuous data. Let's say if you want to classify them into 10 classes, you will see in the literature people have classified maximum to 10 classes. I have used sometimes about 4 classes. Okay, as an input data. So then how do you classify them? Based on what? GIS offers you to do classification automatically by using different types of method. Okay, one is area-based classification, equal area-based classification. Another one is what? Quantile-based classification. Another one you have some other also natural grade classification. Okay, then you have standard deviation-based classification. Too many of classifications there. Question is which one you use? Okay. Again, this needs actually for you to do the research. In the literature, what is being used. But again, there are many people that have used different types. So I always have been using quantile-based classification. Okay. So I always used to use the quantile-based classification. So if you want to represent the landslide analysis steps, so there are 3 steps. So forget about landslide. Any kind of assessment you do, landslide is just one of the examples. So that means this is not just for the landslide. You can do forest fire, you can do flooding, you can do for like soil erosion assessment, groundwater potential mapping, mineral perspective mapping, etc., etc., etc. Okay. So susceptibility is a function of inventory, okay, landslide inventory, and the landslide conditioning factors. Correct? Hazard is a probability, 0.1. Okay, that is a function of susceptibility and the triggering factor. Okay, whether it is rainfall or whether it is seismic amplification. Okay, the risk is a function of possibility damageable object. This is how when you want to. So yesterday we have learned actually the detailed way of doing the risk assessment, but more often than not, it's very hard to do that way because of the lack of data set. Right? So therefore, we make it a very simple way of also calculating the risk. It's again quantifying the risk, which is the possibility. Possibility is actually hazard. Then you come with the damageable object, means elements of risk. And if you want to multiply again by the value of the risk, also it's possible if you have the data. Okay, so accordingly you must produce the data, and I mean the map should be correctly named, whether it's quantitative versus quantitative risk, qualitative risk, and so on. Okay. Now, for this particular application, let's look at actually what are the input data that is there. Landslide. So what are the attributes actually you can have when you are creating the data in GIS? Yesterday you are learning how to create data in GIS, right? As a shapefile. Okay. So for example, landslide in the attribute. So you have the feature, right? Then you have the polygon on every point. What you should have: date, type, activity, depth, dimension. So this means all detailed information about the landslide you must capture it in your GIS database. Okay? How you get it? From field survey, aerial photo survey, satellite-based image analysis, and so on. Okay? Geomorphology, basically you can get it from them. Most of the parameters, geomorphological variables, can be derived from digital elevation model. Okay? So, freely available digital elevation model, you can use it, like Alos Pulsar, which is 12.5 meter, or maybe some other type if you have lucky enough, and if you have a database, then is also available. Or maybe 5 meter, I don't know, Bhuvan has, for the entire country, they have also the digital elevation model. What is? Anyone? Cartosat, I think it's 5 meter? 30 meter? 30 meter is already there long time ago. Okay. 5 meter is also available, paid. But for the research purpose, I think it's for free. No? You'll have to pay. But it's very minimal. Maybe 1,000 rupees. Okay. So, geomorphological units, altitude, slope direction, slope length, curvature, all these things actually should be derived. And they also can be derived from topographic map. If you have nothing, if you have digital topographic map also, you can calculate the triangular network and you can produce the either raster DM or clean DM. It doesn't matter. But ultimately we will be using the raster DM. Okay? Engineering geology kind of data, lithology, soil, structural geology means faults, fault lines, okay, lineaments, seismic acceleration, like PGA, peak ground acceleration map. Okay, every country they have produced actually the PGA map as well. You can take them and you can use it. Or you can produce on your own because the data is there. The USGS data set is there for 100 years or more, maybe more than that. Okay, so you can use that. So in lithology, what you have? Lithology, rock strength, discontinuity spacing, depends what sorts of data that you have. But it can span, it can just go on, depending on how much detailed data that you have. Soil, material types, effective depth, then parent material, drainage, structural geology, fault type, length, deep direction, fold axis, etc. etc. Okay. For forest, if you have the detailed data such as wood type, age, diameter, density, okay. For land use, infrastructure or different type of land use, road type, railway lines, urban area, land use types, agricultural, okay, different types of agricultural, what are the crop types, as much other data that you could derive, okay. Or you can generalize depending on what kind of assessment that you are doing, okay. Then hydrology. Basically, you get the meteorological data. Okay? Then you have a drainage basin and all those things also you can be able to produce. And here I have mentioned what are the data sources that you can possibly refer. Okay? Now, this is the overall methodology. So you have data collection, you do satellite image, 11 photographs. From satellite image, you can derive the land use land cover map. From field survey, if you are going to the field and extracting actually or verifying your landslide locations, obviously that's the landslide occurrence map or inventory map. Then from them you can extract slope, aspect, all those things. Okay. Now make sure all the assessment has to be done in one cell size, pixel size. Okay. All the data should be tracked in one cell size. If it is 10 meters, it's 10 meters for all. Okay. Sometimes the lithological map, you wouldn't have actually very detailed, maybe 10,000, 20,000, it's not needed. Right? Because how much does it vary? The lithological information doesn't vary much. Right? So you can convert it, you can resample it from whatever input data into the desired input data that you are using, the cell size that you are using. That is absolutely no problem. But you can't do it for land use land cover data. Right? Because land use land cover changes so quickly, right? Within 2 meters the land use changing. This is a different type of crop types. There is whether there is a settlement, whether there is a wooden house, there is So you must logically think of it. Not just putting everything under the carpet, try to do the assessment, blind way. No, not right way. So then use the sampling and then you use the probabilistic based method. Now let's look at it. So everything is done as layer based analysis. So what do you call the thematic layer, right? So each of these conditioning factors they have been prepared as individual layer. Okay. So here you see all the thematic maps, input data, all these. Then you have each of the thematic maps have got attribute table also. And attribute table is very, very important. Because that's why actually it provides you the information about what. Alright?
Yes.
Then this I have just given you a simple change analysis because if you do not have, let's say, inventory data, you can also use the archive satellite data to do the change analysis before and after of a landslide, and you can also do the assessment. I mean, you can also estimate the, or you can derive the landslide location map as well. Okay? I'll show you some examples also. And then this is being used as a training data. Then, obviously, here I have mentioned neural network, but you can use any method, either probabilistic, logistic, or neural network, support vector machine, random forest, or gradient boost, or whatever, deep learning, whatever. Okay? This is how it works. That means you have all the input data, then you have actually this is the dependent variable, which is landslide, and many independent variable. Then you do the quantification in the raster-based assessment.
Sir, how I identify which model is suitable for given data?
Data, or which model is suitable for the given application?
How मतलब कौन सा मॉडल मुझे लगाना है सर डेटा के लिए, मुझे कैसे पता चलेगा?
मॉडल डाटा के लिए मतलब मैं समझ रहा हूँ।
कौन सा मॉडल is perfect for my work?
हाँ, कौन सा मॉडल suitable होगा?
तो इसलिए मतलब application की बात कर रहे हो ना?
हाँ, yes.
Whether someone is using working on earthquake risk assessment, someone is working on landslide risk assessment, or someone is working on flood susceptibility assessment. You are asking about that, right? Yeah, that is no hard and fast rule. But fast and fast, like जैसे कि हम लोग गणपति से शुरू करते हैं ना, ऐसा ही we must actually start with the frequency ratio model, because this is simple yet very powerful, and it gives you a lot of information that whether it makes sense or not. Some of the input variables, whether you have selected, it makes sense or not, can be known through this simple probabilistic based model. That's the first step. You use that. Then you know that, okay, there are some correlation exists or not. Then go to the next step. Any model that you use.
तो और चीज़ कर सकते हो, एक्सटेंसिव डिटेल से नहीं मुझे मेरा जो स्ट्रैटेजी है उसका जियोमॉर्फोलॉजिकल कंडीशन और फिजिकल कंडीशन क्या है उसके ऊपर जितना भी पेपर आया वो करके देख सकते हो, मगर वो फिट नहीं करता।
Data set is different. The number of data is different. The number of variables are different. The scale is different. How can you use it? That's why I'm telling you, there are no hard and fast rule. But still, for the literature, we are introducing new type of methods, right? If you look at my latest paper, always there has to be something new, a novel approach, a new
सर
method.
मॉडल चेंज होने पर एक्यूरेसी भी चेंज
होती है, yes. But I don't bother much, because see, you have to understand the data-driven based assessment. Okay. For example, neural network. What it does? It's a training the computer, right? उसमें overtraining भी हो सकता है, right or not? अगर overtraining कर रहे हो, overfitting भी होगा. That means overprediction भी होगा. Overprediction होगा तो accuracy ज़्यादा आएगा, but not necessarily they are. You can use those information, then they may not be accurate, right or not? So it's a very robust and conservative approach of making these outputs are very important. It's not about he got 98 and I am getting 99. It's fantastic. No, because spatial you will understand once actually you go more and more, because how you calculate actually the validation process. Once you understand that, then you must bother that much about the accuracy. Okay? Because 80%, 85%, 90%, because people are obsessed actually with this accuracy in terms of 90, 95, 98. But this is just a mathematical representation of a number. But logically, does it make sense? How much of false alarm that you are giving, that is also very important.
तो वही उनका कंक्लूजन होता है कितना आया तो ये बेस पे
Yeah, but you see, when you do, like me, when I am doing some scientific analysis, when I am introducing, so I am also introducing some tools and algorithms and methods. But I am not recommending that actually you use it for this purpose. But when I do, for example, a consultancy project for a government, which I have done for multiple countries, there my approach is totally different. There I wouldn't actually use all this hi-fi, fancy models. Okay?
Yes.
Okay, so now you do actually the raster based assessment to produce the susceptibility map. Any questions you have before we go into this case study? No? I think it's clear, right? Nothing much difficult. So this is a case study in Korea, South Korea. Now look at the study flow. What we did here. In the first step, we created the spatial database. About 1,800 landslides were established from different sources for the study area. Okay? Now, this data was split into randomly into 70 and 30. 70 in GIS, any of the GIS software you go, you take the input data and you can ask them actually classify randomly to do for it. That's not a problem. Okay? So, then 70% of the data was used for training, 30% was used for testing. Okay? Then we apply the frequency response model to calculate the relationship between the inventory and all those independent variables. Okay? Understood? Then we did the verification or validation of the map. Okay? This is the study area. You can see this is the dam. Dam varies from 490 meter to altitude varies from 490 meters to about a kilometer, 1,200 meters. Okay? And these dot points that what you see, those are the landslide locations. Okay? Pay attention because this is regardless of the application that you are using, the steps follows the same. Okay? Now, inventory. I say that how do you calculate, how do you derive an inventory? If you are lucky, if someone just gives you, no, take it. You wouldn't get like that. There is no ideal conditions. Right? You got to prepare. Papat pelne padenge. Again, so got to go here, go there, collect from there, verification, and then do that, this, that. You know, cleaning the data, all these things you have to do. So in this case, because this is a project we did long time ago, we took the analog aerial photos. We had the data for the entire country because they take it very frequently. This one photograph. You know. Then analog aerial photos, then digital aerial photos, field survey we did. So mixing everything that actually come with the 1,800 landslides. Now, look at the interpretation from the digital aerial photos. See, for example, this is a forest area, upslope area. This is some factory here. You can see there is a scar area, right? This is a scar area. So we went to the field and did actually the field validation. Once we interpret here, went and double check, okay, this is a landslide.
Sir, time.
तो आप कुछ नहीं हुआ आज मेरा एक ही लेक्चर है एक्चुअली सेकंड वाला मेरा था बट दे वांटेड मी टू हैव अ मीटिंग विद द डायरेक्टर सो ओके टाइम कहाँ चला रहा था मैंने समझ नहीं ओके नाउ यू सी दिस इज द एनालॉग digital map, analog map. You can see here. Why did I delineate as a landslide? Anyone tells me? See, this is not a scar. Some vegetation has happened.
Yes, sir.
But a previous landslide where the revegetation has happened. So by looking at actually the texture of the vegetation, okay, contrast of the vegetation, because these are new. So that means the old vegetation, they will be having different kind of reflectance. Now this is the new vegetation that has happened. So that reflectance value is going to be different. So that is a susceptible, that you suspect that is a possible landslide. but you're not 100% sure. That's why you go to the field and make sure that it's yes, it's a landslide. Okay? Research is not easy. You think what? So, इधर से डाटा आ गया, उधर से डाटा आ गया, हम कंप्यूटर में बैठ गए, हो गया 2 दिन में पेपर लिख दिए, बन गया, ऐसा थोड़ा ना हो. Okay? So you see, that's how demarcated actually the all landslide locations. See, here. See here. See here. This is what you call visual interpretation from the aerial photos or digital photos. But that needs validation. Okay? You're not 100% sure. And you wouldn't know also where exactly, because the vegetation has happened, right? You don't know where exactly. Okay? So you have to make sure you go to the field and collect the data. Okay, now this is done. Another way is when you do the change analysis. If you have dam, let's say the dam was prepared 5 years ago, and you have a new dam. So you just do a ratioing of the dam or minusing of the dam. You can also see the areas where the material has been detached. There are many mathematical models that they use it actually to calculate that. That also you can do that. Or if you have like Google Earth Engine, you can do and take a look at the temporal data and you see that any changes that has happened. Based on this texture information, contrast, texture, those kind of things. Okay. Next is spatial database. Then you categorize all the data. You see, now I put it here. Look at this table. Number of total landslide is 1,801. Okay. Cell size, I fix it at 10 meters. Why 10 meters? Because the given input data, they are all in the good implementation of the 10 meter. Okay. I have not taken data that is input data, which is 1 to 1 million, and then I am making it actually into 10 meter. No, this is wrong. Okay. So here I put the cell size 10 meter. So obviously, जो मेरा दायरा है, the study area, number of total cell came around 597, this much, 6 lakh almost. Number of columns, this is the number of rows. Okay, this is for the study area. Not study area, my analysis area, which is a square, isn't it? Because there will be also a lot of area which has no data. Because your study area is not square anyway. It goes like this, right? So no data is excluded here. Okay? So what's up?
Sir, this cell size मेरा यूनिफॉर्म मैंने 10 मीटर बाय 10 मीटर सभी में रखा. बट अगर स्केल मेरा 1:25,000, 1:50,000, उसमें अगर मेरा वेरिएशन है तो उसको ओवरले कर सकते हैं.
No, you must convert into 10. That means, see, geological map, it's a polygon data, right? It's a vector data. So now I convert into raster. When you convert into raster, it would ask you what is the cell size that you would like to see. That's where I put it 10 meter. But as I mentioned previously, you can do it for a geological map because geology doesn't change. एक ही एरिया में कितना 3 या 4 टाइप का लिथो होगा, कितना हो, right? So that's why. But look at the land cover map, 5,000 scale, and for 5,000, I am actually now oversampling to 10 meter. Understand? Because 25,000 is considered as 10 meter. Okay. So now, you see?
Yes.
And then you have other maps are all 25,000, which is now you're understanding how to define the scale of your analysis. Because that is why. Otherwise, I have seen a lot of papers, a lot of outputs. It's all being pixelated. It's all rubbish. I see that, I reject the paper immediately. I don't have to even write any comment. Okay? Okay? Good. So understand this?
Sir, one more query, like, what will be more logical, like, if we shift, if we change all the scales to 1:5,000 or?
No, you can't, because then you are, it's what, undersampling, oversampling. Bochoti. If you have input data 1 is to 100,000. Okay, your land use map is 1 is to 100,000. Yesterday I was telling you, the day before yesterday I was telling you, when we are talking about the resolution. Remember those raster area and all that. 1 is to 100,000 means essentially is what? 1 pixel size is about, let's say 100 meters. 100 meters. Okay. Within 100 meters, now, if you are talking about land use, that could be दो तीन field हो सकता है. India में what? Some of the fields are also very small, and how many houses can be there, and all that. So there won't be any actual representation of the. Now you have in 1 pixel there are mixed representation of the features or objects, which you wouldn't like to do that. Okay, but in the case of lithology, you have a fixed boundary. Regardless of the area, it's one type. Are you getting me or not? Yeah? So I wouldn't bother. Soil, I wouldn't bother. Soil map, you wouldn't get that detail. But other type of information, obviously, very good. Okay? Good. We must finish this, otherwise the momentum would be less. Okay? I don't have lecture today. Alright, so this is clear. You see, from individual data, we extracted all the parameters, then what are the data type, and then the scale. You might have seen these kind of tables in the papers. Okay? And spatially, how do they look like individual parameters? Also, you would have seen that in the papers. Because we talk about, when you are writing the paper, when you are writing the thesis, you must explain why this particular variable that you have selected. What is the relationship between this variable and the kind of hazard that you are analyzing? That explanation has to be there. Also, not because actually someone else has used, not just by giving reference to literature saying that XX Pradhan et al. Has used and I am reading. No, because you are dealing with a different study area. So you've got to bring a discussion there. That is why actually your descriptive statistical analysis like frequency trace model can help you to explain why have you taken it, this particular value. Okay? So slope in unit, these are actually different classes, and you can see that 10 classes, and it is quantile classification. Then you have aspect, again, you have 9 classes, including the flat area. Okay? Curvature, you have 3 types. Again, what you do, when you calculate the curvature, it comes in the values. It doesn't come actually, it comes values in a wide range of values. Then you reclassify it into 3 classes. That means negative until 0, 1 plus, 0 is 1 plus, okay, and greater than 0, positive of another class. So, convex is positive, concave is negative, flat is 0. And again, you've got to explain that why. Because why curvature plays an important role? Because when it is a convex slope, what happens is that it is all being exposed also, and the surface runoff is very high. Water flow is high, surface runoff is high. Infiltration is very low. But in the concave, the infiltration is much more, the water retention is much more, the groundwater table is more likely to be closer.
Related to flow accumulation.
Yeah, flow accumulation, right? So all those things you need to explain. Hence, these variables has been selected. Then you give actually the references. Understand? At the same time, also I am telling you how to write the paper also. Okay. So curvature. Then you have topographic wetness index. Again, wide range of variables will come, classify into quantile classes. 10 quantile classes. Then stream power index, again classified into 10 quantile classes. Distance from lineament, this is also a bit dicey. Now, again, depends. Some areas where the seismic activities are not much more, how do you define what is the distance that is more likely actually? You see that the closer one is very, very susceptible to landslide, or it can trigger a landslide. Right, all these variables you are taking it, hoping that if the triggering factor happens, then this could be susceptible. Right, and then you are assigning the weightage. Correct? So in this case, not knowing what would be the accurate representation, we just quantile basis. We just took the quantile basis. But some people, specific agencies, they have their own guidelines. So basically guidelines, they take the classes. Okay? Now, what is TWI? SPI. TWI basically is being calculated logarithmic of, what is this? Alpha is actually the upward slope divided by the tan, that is actually the entire slope area. Okay? And this has to be all converted into radian. Right? Isn't it? Very simple. I mean, all these softwares, they allow you actually to derive this. So flow accumulation basically you must calculate first. Okay? And then you derive this equation. Similarly, that is TWI, wetness index. Stream power index, this is logarithmic, it is tangent. Okay, of the flow accumulation. Okay? All these GIS softwares allows you. Saga and all these GIS softwares allows you to calculate this. Okay? We have time means we will do this. I have some data you can practice. But I don't have patience to teach one that. So someone has to have. Okay? I have done this maybe 1 million times, so I get bored. Okay, geology, see here only a few times. Land use, different types of land, you see how digital the land uses are. See here, how many classes, right? Residential area, industrial area, commercial area, transportation, utilities, paddy field, blah blah blah, other type agricultural, then different type of forest, natural grasses, these things. So the more number of actually very different type of land use you have. Okay. Then this is timber diameter. This is timber type. The timber also is it strengthens the soil. Okay. Timber like in the forest, timber actually provides a lot of keeps intact to the soil. Like how you have the mangroves basically protects the coastal line. Timber density, timber age, so obviously you don't have this kind of data here. Then topography, like this is what the geomorphological, like pediments and like buttas or all those kind of things. Okay. Then soil drainage, then soil material, soil thickness. I don't think we have this so detailed data set. Maybe you have soil type. Texture you have, yeah. Soil type and soil texture, okay? But here you have soil material, soil thickness, soil texture, okay? And you look at the soil texture, how many types here? Now let's look at you just log this and we'll finish it, okay? Next one is probabilistic model. What we do? Look at this. A very simple example that I have given. This is the study area, let's say, and the study area has 10 rows by 10 columns, assuming, okay, 10 rows by 10 columns. Now let's say one particular type of, we are now doing the frequency ratio analysis, you have to do it for individual, okay, the dependent variable is the landslide location with respect to the all independent variables, okay. Let's say the individual variables here is one of the independent variables here has 3 classes. Let's say geology. Okay, lithotypes. Class 1, class 2, class 3. Let's say sedimentary, metamorphic and igneous. Okay, to make it simplified. Now this is the spatial distribution of the location of the landslide, the red dots, because now I overlay, right? The landslide locations has now been overlaid on the top of the soil, the geology map. Let's say, assuming this is the geology map. Okay, now in class 1 of geology map, geology class, how many landslides has happened? 4. In class 2, class 3, 3. Okay. Now we do the simple raster based descriptive tabulate area analysis. I use the word tabulate area analysis. In GIS, in ArcGIS, in all kind of GIS software, you will have something called tabulate analysis. Okay? So total classes, now you look at the table here. Total classes, you have class 1, class 2, class 3. Okay? If you look at the number of pixel, percentage of pixel, it's very easy. Class 1, how many pixels you have? See, 8 multiplied by 4, 32 pixels, right? Right around? 8 by 4. Okay? Class 2, you have 30 pixels. 6 by 5. Class 3, you have 38 pixels. That means this whole shape there. You can see here or no? This one. Class 3 is where? This, right? This is class 2, this is class 1. Okay? So now you know number of pixels, percentage of pixels is very easy to calculate. Now the percentage of landslides. Also very easy. Class 1 you have 4, class 2 is 3, class 3 is also 3. And the percentage is very easy to calculate. 40%, 30%, 30%. Here also percentage is very easy to calculate. 32%, 30%, 38%. Frequency ratio is just a simple ratio between the number of percentage of landslide divided by the number of pixels. Okay, that means what happens? 40% by 32%, you get the number 1.25. 30% by divided by 30%, you get 1. Then you have 30% by 38%, you get 0.7. The rule of thumb says when the number here, the frequency ratio value is greater than 1 or equal to 1, it shows a positive relationship between that particular type of class. Okay? Mathematics. Less than 1? No. The higher the number value, obviously it is much more positively correlated with that particular class with respect to the inventory. Okay? When you start any kind of model, start with this model first. You understand about your data, you understand about your inventory, you understand about area and so on. Before going into the fancy machine learning based model. Okay?